Interesting. Do. All right. So, I think we're in this. So this is fun. Anyone else want this? Like 2 minutes, I guess. Poor turnout. I guess. Well, what can I expect? Hi, Jason. Howdy. This is fun. So, I think give it a minute. Oh, hey, Mark. How you doing? Oh, hi, Johnny. This is fun. So, how's your guys' day going? Well, that delay is serious. Oh. Call of Duty Warzone is lit. Yeah, I agree. I haven't played it, but that's good. I had the original MW. I mean, it has to be better. I'm more excited for MW2 than I am for Warzone, but yeah, that's beside the point. Not surprising. Let's start. I mean, delay is pretty bad, so makes sense. Yeah, you can't live chat with anybody. You just gotta kind of keep an eye on this question. Good thing I have it open. Man, it's so bad. I wonder how people actually do this in real life. It's kind of a pretty big question. Oh, fun times. It's water, guys. Don't worry. I'm learning machine. Well, I'm machine learning. Well, in both cases, there's a lot to learn, right? Kind of really boring. Just kind of here by myself, talking to myself. Encore says lol. Respectable. That's a very good response. Anyone notice the weather today? It's like raining and stuff. It's weird. I don't like it. I thought this was really California. Like, we're perpetually in a drought. It's not supposed to rain. Machine learned. Alright. That's too far. I'm getting lit in Warzone. I can't play Warzone. I have Linux. So, I'm actually kind of curious. Can you play Warzone on Linux? I have to use Wine. Nah, screw that. That's too much work. Best weather to go out. Yikes. I mean, the weather's pretty similar to like how Seattle is, or like London. So if you're working for Microsoft or any company based in Britain, it's gonna be like this. It's gloomy. It's got Red Red Redemption is it's definitely a play. I haven't played it yet. I'm trying to, but man, I just don't have time. I wonder if there's a way to get rid of this delay. Like, why is there a delay? It's not like we're that far apart. It's like a 2-minute delay too. That's horrible. Maybe that's something we can spend our money on. Figure out a way so that we don't get a delay. That's a rhyme. Call me the rap god. Hey Mark, do you go home? By the time you get this, we'll probably have started, but just out of curiosity. Hello, Brian? One more minute, guys. Let's see. Oh, that's useful. He's home right now. Cool. Feels bad. How about you, Brian? Did you go home too? I mean, going back to Folsom's pretty far, so. 6:40. All right. So I'm going to start just because this delay is horrible. I kind of want to get through this so that I can sleep. But welcome to UCI's first inaugural stream. Kind of a lot of bugs to work out, but hopefully everything goes smoothly today. I don't see any problems, knock on wood. But this is going to be kind of an interesting one. anything does go wrong, please be patient with us. Thank you all for coming out and actually, responding to the reminder on YouTube. But today we're going to be doing something kind of cool. Recent years has been a technology known as DLSS, or Deep Learning Supersampling. And it's really revolutionizing the way that we're handling computer games. And so one of those kind of trademark steps to getting to that point, a pivotal point when we're getting into, increasing resolution using a neural network, right, which is the foundation of DLSS. One of those major kind of topics and areas that we focus on is super resolution. So one key difference between super resolution and DLSS is that super resolution doesn't focus on performance. It primarily focuses on, it's like a broader field dedicated specifically to improving image accuracy and fidelity in a lot of states. So kind of moving into the GAN part, right? So what does a GAN stand for? GAN stands for Generative Adversarial Neural Network. And so what that means is we have, the problem that we're trying to solve is to create information out of nothing, right? Or very limited information, I should say, right? And so one of the few jobs that these types of architectures do really well at is, again, generating information, right? Or rather extracting information that we may not have actually originally seen, just by the naked eye, right? Something that machine learning does really well is that it kind of confiscates this issue of what we perceive as an impossible task and simplifies it to a very small but minimal machine learning model. And in this case, we're using kind of a similar technique, right? We want to create information or present information that may be deeply embedded within whatever input is. And that's what generators do really well, right? Adversarial technique, right? One of the big things about neural networks is they do really well at simple tasks, right? With generating information, with representing and producing information in a very concise manner. But the problem is they do it too well. And so we find that there's a fine line between human experience, right? A metric where we're trying to focus on kind of how the human perceives the type of information given by the neural network, and the statistical model, right? The basics of how do you train these neural networks, right? Which is basically just a math function. And so kind of balancing these two, right? Because if we have a model that does too well statistically but does poorly in a human evaluation, then that model is essentially useless to the end consumer, right? And so we need to figure out a way in how to kind of fix that, right? We need to come up with new mechanisms to evaluate models that are non-empirical, right? And so that's kind of one of the reasons that in 2014, Ian Goodfellow created GAN architecture, right? Generative Adversarial Networks, right? It is kind of this it boils down to this kind of cops and robbers model where we have two neural networks competing with each other. The neural network A will basically, who is the cop, right, tries to determine whether or not neural network B is producing a real or a fake output, right? And that's the generative part. We're trying to generate information from nothing, right? So we need to prove that that information is real or fake, right? And so that's really the adversarial part, right? That's the adversarial terminology being used there, right? And we actually coined that term elsewhere, right? We call adversarial attacks. And this has become much more popular as a technique to reinforce neural networks, right? To make sure that whatever being created, right, can and will basically it will be, whatever model is being created is robust, right? We want it to be secure, because if we have a fake model that doesn't really work that well in, our next autonomous vehicles, then we leaving our lives and the lives of the public in, in a state of kind of imbalance and like incorrect ways, right? Sounds like an agent actor kind of model, which is used in reinforcement learning. Yes and no. It's correct in the sense that we have two agents that are trying to accomplish a similar task or goal, but it differs in what those, like, they're trying to produce a neural network. Like, basically what we're doing is, in a reinforcement model, we can have multiple agents essentially competing for similar resources, and the dominant model will win, right? Yeah. But, when it comes to GANs, we want both neural networks. We want basically, both neural networks to essentially develop together and complement each other. And that's kind of the benefits of an adversarial attack mechanism, right? It's to have a neural network, create a neural network that can combat erroneous data, right? We often do adversarial attacks against a machine learning model, or sorry, image classification models, as well as deepfakes, actually. A lot of adversarial attack type methodology has been developed for deepfakes, because we as human beings can't really discern the difference between deepfakes, but a machine can, and that's where, like, an adversarial attack type mechanism is really powerful, because now we can create neural network models that can combat that. Right? I don't know if that makes sense, but I mean, yeah, like reinforcement models, there's a different end goal in mind, right? Whereas in GANs, we typically just want two models that are really powerful together and complement each other, right? And I'll get into the importance of that. It's kind of foreshadowing, but I mean, this is a general architecture for GAN. We have an input metric, right? Input vector that gets passed into a generator that generates fake data, fake images, whatever. And then we compare that against real images, real data. And we produce a predicted label, right? Is it real or is it fake? And eventually, both neural networks will grow together, and the generator will be better at creating better fake images, right? That will fool the discriminator. But the discriminator will also be learning how to detect those fake images and will become better at doing that, right? It will continuously be looping to grow. So, like, in essence, it's like, they're both growing up together, I think, is the best way to put it together. Yeah. Of course, coming up with this architecture comes with a lot of caveats, and here's like 4 primary ones. You have 2 neural networks to train, right? Neural networks are as themselves are very finicky, right? I think a good analogy is rolling a ball up a hill, and if you let go, the ball is just going to crush you, and if you push too far, the ball is just going to keep rolling down the hill, right? So it's like, once you get it to the top, then hey, you're successful, but getting it there and finding that balance is very difficult. And if you have to do 2 neural networks, it's very difficult in its own right. Another thing that often comes up, and there are techniques to mitigate this, is that one neural network becomes more powerful. And in that sense, then you're developing a reinforcement agent kind of mechanism, right, where one is competing against the other, right? The compute, that neural network, like let's say the generator becomes very powerful, then whatever output the discriminator gives is completely useless to train the generator. So the generator just keep getting better and better at making fakes, but not fakes that humans can recognize, fakes that the discriminator recognizes. Right? Then that defeats the point, right, of making a GAN, because we want neural networks to be, in terms of human experience-wise, much more better in tuned, right? We want them to create outputs that humans can understand, rather than just having statistical models dictate that. And of course, another thing that since you have two neural networks, you have a huge compute requirement, right? It's very tricky to manage resources, and we'll go over kind of what I did and the tricks that I did, and also the neural network architecture, like the differences between what I have and what is being presented in the collab. And also, of course, there's an issue of easily overfitting and underfitting, and that kind of goes hand in hand with one of the neural networks becomes more powerful. Sometimes the discriminator will underfit, and therefore all images produced by the generator become real. Right? That's not a good balance. You want to have that equilibrium. Other times you'll have neural networks overfitting, right? Or most often you'll have the generator that overfits, right? It creates an image that's too perfect. And so when we humans look at that image, we're like, oh my God, this doesn't seem right, right? There's an uncanny valley. And we can kind of go into that. I've kind of discovered a couple of artifacts with my models, the pre-trained models. And so we'll go over what those specific caveats are. So to get into our neural network that we're going to build today, well, not really build, we're not going to build it. I have already built it. We're going to build the training loops, because that's the most important part, right? Understanding a GAN is really the loss function. What does that represent, and how do we implement that? But in our situation, we're basically using two primary neural network architectures. So we have a generator that's based off of ResNet 50, and we have a discriminator that's based off of VGG16. And both of these neural networks will work together in tandem. But of course, in order to mitigate the previous mentioned errors, we need to kind of compensate for this somehow, right? And so here's my trick, or rather the trick of the paper that I've just described to you, right? The trick is we're going to have a third neural network, but this neural network's not going to train. It's going to act as the referee between this bullfight, right? It's going to be the person, the neural network or the architecture that is static, right? So it doesn't really train. But we're going to have the generator also pre-train, right? So what that means is we're going to initialize weights, right? It's very difficult to figure out what weights to initialize in these neural networks because the data could be very different, right? And so one good way is to prep the generator so that we get rid of the first 10 epochs, right? We reduce that amount of overhead that needs to be created in order for this process to work properly, right? So that we can both neural networks kind of start on even footing. It's like equalizing the playing field so that they both train at the same time. And so, yeah, basically that's the end of the presentation. It's kind of difficult to answer questions because of the delay. But I guess we can start on coding. Let me just make sure this works. That is awkward. Oh, switch accounts. Cool. So I'll wait for everyone to catch up, actually. That'll be a good idea. So it does work. Good to know. Wait, it's the right one. No. Oh, this is the wrong one. Oopsies. Let me get you this one. Get shareable link. Oops. Tiny. Oh no. Oh, looks like my camera died. So let me Let me kill that. Okay, so then let me switch this over to this one. Nope, that didn't achieve. Need to the third static model. Can you post the notebook data URL in the? Oh, that's actually a really good idea. Why didn't I think of that? Okay, can you not? Let me just do that. Copy link. Perfect. All right, so the third static model. Okay, so we are basically what we're doing is, so in order to combat the issues with having a neural network overpowering another neural network, we want to have a set point that we don't need to kind of fight each neural network, right? So we want an even playing field in a sense. And so to do that, we need to create a fixed point which both neural networks can kind of train off of. It's easier in practice when we go into the code. It'll be easier to show you and explain exactly what the probable thing is. But let me make sure. Did we get it? This is fun. It's like I'm tired. I'm talking to a ghost. Yeah, I don't think you get too good an explanation. But, see, are you still running? Yes, you are. Good. Man, this is tough. I have no instant feedback, so it's like I don't know how I'm doing. Yay, the link works. Yay. Okay. This delay really isn't helping. You might want to try Zoom instead. Yeah, I might want to try Zoom. Ooh, that might not be a bad idea. Sign in. Okay, let's first, I'll do. Yeah, we're trying to set up Zoom because this streaming stuff is very difficult. Because the expected output doesn't really work that well. Alright. Yeah, this is kind of a fun time. Okay, so let's try something. Might be dumb, but might be doable. I'll be right back. Alright, it's fine. Okay. Make the code bigger on my browser. Okay, I will. Jason, you gotta tell me that beforehand, man. You got me all confused. Does this work? I could just maximize it and keep on going. Okay. Where were we? All right. I guess we gotta do some stuff. Let's see. Yeah, so I'm assuming everybody's kind of figured out their stuff. Here, let me go to OBS and get rid of that little box. We don't seem to want to. Yes. Perfect. Cool. Yeah, my bad. OBS crashed. So, anyways, yeah, okay, so let's try this. So, we're gonna basically install the collab TQDM repository. There's all these dependencies. So here are the hyperparameters that we can adjust. Basically, whenever you want to go back and change anything related to the neural networks architecture, you can change them here. And then here I have all the data kind of pre-processing and processing set up here. All right, this is actually just downloading the data. We don't really need to worry about that. So we can just run, we gotta run this cell first. Yeah, just ignore that. It's a warning. No one needs to notice about it. No one needs to care about that. So it's gonna take a minute. It's a pretty big data set. It's 800 images of 2K resolution. So it's a pretty big deal, or a big data set, I should say. One thing to note here is that this is resolution of 56 by 56, right? So our low resolution image that we're going to now upscale, we're starting with 56 by 56 image, and then we're going to upscale it to 112 by 112. All right, good. All right, so I'm just going to wait for this to download. Shouldn't be more than a minute. Yeah, sorry guys. I mean, it's kind of a difficult thing to deal with, streaming and stuff like that. So it's especially since it's our first time. Yeah, but thank you all for putting up with it. It's good too. Zoom in a little bit more. All right. Yep, it's a waiting game. This is fun. I saw 69. That was funny. Yeah, I gotta say, I do like in-person meetings. It's a lot more calm. This is just annoying, but fun, I guess. It's kind of fun. Oh, one data set is done. Just gonna get the other one working. Just gonna be a minute. In the meantime, so here's the model. Basically, we have a discriminator. This follows the VGG16 architecture. Here we're using the VGG19. This is called the feature extractor. One thing to note here is that we're not actually using the entire model. We're in fact concatenating. We're only using 11 of the something like 30 layers or something like that. And the reason for this is because the latter part of the model does not. Oh, did it crash? No. Okay. The latter part of the model does not really need to deal with. Well, the latter part of the model is designed specifically for categorization, and we don't need the categorization part, right? All we need is just what are the features available in the image, right? And if we can preserve those, then that's a great thing. Previously, we used to use eval. Basically, we'd make this VGG19 an evaluation model, but nowadays we find that there's no need for that because the adversarial loss alpha value is pretty low, so it doesn't really affect too much the overall performance too much. So we don't really need to do eval on this. That just complicates the writing of the code, but at the same time, we can also tune this model as well as we're training our discriminator, right? And this serves as a discriminator, just if I wasn't clear. This is a discriminator. And this is our primary discriminator, the one that's trained fresh. There's no weights, pre-trained weights. There's none of that. It's a brand new discriminator. This is based on VGG16. And we're basically building this one from the ground up. And all this neural network does is tell whether it's a truth or a fake image, right? That's all it does. And we finally get to the generator. This is based on ResNet 50. I mean, it's a little bit chunky and there's a lot of stuff to kind of break down, but it basically boils down to a ResNet 50 architecture. The only difference being the last few layers aren't like for classification or bounding boxes or stuff like that. It's mainly for upsampling, and we have a little something called upsample block, which is another here. Yeah, upsample convolution. So we use a special kind of convolution that we call it's not pixel shuffle. It is subpixel convolution. And what that really represents. So typically in a case where we want to upsample images or increase the resolution, we use a convolution transpose. But in recent light of important of performance, we need to focus on what we want to create the fastest kernels possible, right? We want to use the fastest kernels possible, and so convolution transpose is very complex and compute heavy. And so rather than using that, we've created an alternative, which is this subpixel convolution that we've devised here. And then, of course, the residual block, which is from ResNet. You guys would familiarize with them. And then we're using a special operator called swish instead of sigmoid or tangent. Swish is just, it's defined up here. It's just, x times sigmoid. And that's just based on research. There's a proof about it in the paper if you guys are interested. I believe I have not linked the paper, but I'll show you guys that later. Is this done? Yes, it's finally done. All right, so we built our training data set and our validation data set. Perfect. We also have our model. So we're going to run that real quick to load the model. Perfect. So a little bit of kind of details about the kind of setup here. We're basically going to try and fit everything onto one GPU because Colab only has one GPU. We're using GPUs instead of TPUs. One thing to note that we won't be training the full model because that just takes forever. I think Google right now is limiting resources to kind of extracurricular activities like Colab. They're focusing primarily on the other resources. I think they're strategically putting their resources elsewhere. But generally speaking, it's their VM, so we can't really say much about it. But I do recommend if you do get the chance or have the ability to train this on your own. And I'll show you what the difference between mine and this model right here is. It's really just changing the low resolution. And we'll also go into what that looks like, or what the performance of the model looks like. So a couple of things to note. Again, we have transformations. All this is for converting a 0 to 225 value integer into a floating point that can be understood by a neural network, which is between -1 and 0, right? That's the ideal range. And so that's what we do here with normalization. Unnormalized does the opposite, right? It retracts, it pushes the values between -1 and 1 to between 1 and 0. Right? That's very it. So that's useful for evaluation. So our content criterion. So we're using L2 loss or MSE loss. It's most predominantly found in most image processing type applications. In our case, it's perfect, right? It's exactly what we want to do, right? In the generator, we want to determine whether or not, how close are we to the real image, right? We want to understand that part of that. And so, okay, one sec. And so, MSE is the right type of loss function to use here. All right, Oshi. English, I have a question. Having multiple layers in a network will make it slower to train, right? So if generator was roughly 50 layers, discriminator was roughly 16 layers, wouldn't that cause an issue with the generator and discriminator to train too quickly? Well, it's based on the ResNet. So we're using residual blocks, but does not mean that we're using like a ResNet 50 in particular. In fact, we actually limit the number of residual blocks to 16. So in your case, no, it does not. Again, if we did ResNet 50, that would not fit on any GPU that we could find. That would be way too complicated. Again, you have to support 3 neural networks here, right? And so in terms of memory constraints, it's quite a difficult ask. I mean, even then, if you wanted to say, okay, if we increase the size of the VGG16 to a larger neural network architecture, how would that impact performance? And yeah, that would impact performance, right? It might be slower to train neural network, and it may not yield the same results, right? You might have diminishing returns. I think there is a case study where they used VG19 and discriminator and then increased the size of the generator. It didn't provide that much more results. It just increased the compute performance. So yeah, it's not really 50. And yeah, this is like a non-set value, as you can notice. Whereas everything else is already set, right? So that's the value that we change to increase or decrease the number of residual blocks that we create. But yeah, so we're not really using ResNet 50 is a misnomer. We're using a ResNet architecture would probably be the right way to describe it. Yeah, but thank you for pointing that out. Yeah, so right here. So we're defining the model right here. So we say generator is equal to the generator, and then we have 16 blocks total, and then we're upscaling by some factor. And then you have the discriminator, the simple discriminator, and we call this a feature extractor, and call it a feature extractor, and then we put them to all the devices. So we have a low resolution, we have one's constant, and we'll use these. We are basically using all of these later on in here in this code. All right. Cool. So let's get to coding, I guess. So let me run this one, make sure everything else is running perfect. So now we're downloading VGG19. That one should be a lot faster. It's only 500 megabytes, so that shouldn't be that complicated. So the first loop that we're going to kind of write is the pre-trained generator loop to get a feel for what the process is and how we're going to handle, the data and the pipelining of that, right? So kind of to start, we want to get the high resolution data, right? And that's really coming from our data loader. So the trained data loader is basically taking the div2k set, which is 800 2k images, right? Or 800 specifically 2k resolution images, and then putting that into a fancy memory model for us to use. And then of course we run random cropping, right? We want to randomly crop the image for unique and different sets of data, right? So at the end of the day, we'll get a 112 by 112 tile. That's what I want you guys to kind of understand. And so we'll say high res real, and then of course this one will come with the target data, but we are ignoring that. We don't need that. And then, we can say, so we need to now kind of define the low resolution. So we're going to say for range batch size, we're going to say low res j is equal to, we want to scale the image. That's going to high res real bracket j. And then we also kind of want to normalize the real image to be between -1 and 1. So we'll do that. And J. Cool. So that's kind of the first step. So now we've defined the data that we're going to be processing. So it's as simple as high res real is equal to, we want to send them to the device. So I'm going to say high res real. Dot to generate per device. And we're going to say we're going to now create the fake image, which is going to be created by our generator, right? So we're just going to have generator, and then we'll say low res, and then we want to send this to the device. Yeah, and so that will basically be running the data through, the generator on a forward pass, right? Now we want to define like the loss function, right? So we're going to say gener.0 grad, right, 0 the gradients, and then say generator, I will say content loss is equal to content criterion, right? That's the MSE, high res fake and high res real. Right, so we're comparing the fake image versus the real image and seeing how close they are. And then I'm going to say generator content loss dot backward to call the backward pass on the loss, and then we're going to say optim generator right dot step. Right. So we're now calling the step operation on the optimizer, telling the optimizer to move on to the next learning rate or next step in the iterations. Excuse me. So of course this is, now we're done with essentially pre-training, right? And so we'll just say, we'll run it. It's going to take a minute because I guess Google's latency is pretty bad, so we're going to be here quite a bit. But in the meantime, if anyone has any questions, be a good time to ask. And this delay really does suck. Let's see if I could just ask questions. Let's see. Does anyone have any questions? This delay is fun to deal with. It very much is. I guess if no one has any questions. Okay, I mean, we'll let this one loop. It'll take some time. So now let's actually get onto the training set. So one thing to note here is the learning rate. So here the learning rate is 0.001 or 0.0001. Here it's 4 zeros. And the reason for this is because here we want the generator to train really quickly, rapidly, right? We want it to initialize all the weights. We have it only for 2 epochs for that exact reason, because we don't need it to do more, right? Otherwise, we're just training the generator on its own without this GAN operation process. Right? And that defeats the purpose. And so once we've kind of pre-trained the generator, now we're in equal footing with the discriminator, so to speak. Finally 50%, perfect. Right. So what we're going to do now is put together the pieces. Right. We know there's an adversarial loss. We know there's some type of training loss. We know that there's the content generator loss, right? And we have a discriminator. Now, how do we put those together? That's what we're going to do next. So it's as simple as we're going to take whatever we have here, take it, paste it, because essentially the first step is the same. You want to pre-process the data and create, the real and the fake images, right? That's a good, powerful delay. So what we're going to do next is we want to now kind of develop the features, right? So we want to understand what is real and what is fake, and so we need to define those both archetypes, right? So we're going to say target real is going to, we're going to say just to save this torch.rand, right? We need the batch size, comma 1, and then we're going to multiply it by 0.5 and then add it by 0.7. Why? Because this biases the value towards the positive end, right? It biases it towards 1. It's just a simple math trick. And I want to send this one to a discriminator device. I'm labeling these two devices separately, even though it's the same device, because I have two GPUs, and so I basically loaded one of these model or both of these models into one GPU, and then another model into a different GPU. And so it was really easy just to just change like one number here rather than having to rewrite a lot of code. But that's, again, it's for when you're doing this on your own, and you want that extra oomph. So finally, I'm going to say target fake. I'm going to say torch.rand batch size 1. And then here we're going to say multiply by 3 because this biases it towards 0. Right? We're reducing the bias to the other side. And I'm going to say generator device. Right, so now we've kind of created most of what information we'd want to understand for the discriminator to process. And so one of the few things that we'll need to do is say we need to send this one to the second device, which we really don't, but for the process sake, I'll do it. High res fake is equal to high res fake. Almost tripped myself there. And why did I put discriminator, not discriminator device? I'm just going to copy and paste that. It's all kablooey today. Okay, so now we're going to actually train the discriminator, right? So we're going to train the discriminator. Let's call it D. It's a cool letter. So we're going to say discriminator dot, we're going to say 0 grad. Yeah, that's cool. And we're going to say discriminator loss is equal to, this is where we kind of come up with this adversarial loss. Oops, I did not mean to do that. Right, so adversarial loss in our sense is it's a BCE loss, right? And essentially it's like a categorical loss, binary cross entropy, right? The best way that I can probably describe it is it a 1 or is it a 0? It's like the best way I can describe it. That's what this loss function determines. So in our case, we want to pass the values to the discriminator, right? And so we want to first pass the real target, right? So we'll say high res real, and then to this we want to say high res fake. Oh, sorry, real. And then we're going to add the adversarial loss of the discriminator high res fake, and then we're going to say, oops, I need to say target, not real. It's target real, sorry. Right? So we're taking whatever biased 1 or 0 we're getting here, and then we're comparing that to whatever 1 or 0 is coming out of the discriminator. Right? So we're just going to say that, and let's just change this one to fake. Cool. Yeah. Fun times, fun times. So once we've kind of figured out what our discriminator loss is, then we have one last thing to do, right? Or technically 2 last things, but I'm just going to ignore that. It's really just one last thing, which is to do the backwards prop. So I'm going to do a fancy call here called retain graph. For those who are rich enough to have 2 GPUs, they will thank me. I did all the work for this. So now we're going to say discriminator, and I'm going to say optimizer dot step. Cool. You go here. And I'm just going to say optimizer step. Yeah. So now we've got the discriminator, and what I'm going to do now is going to say, what about the feature, right? We forgot about that VGG19 stuff, huh? But your boy Monish, he's mighty clever. He didn't forget, so let's do it right now. So I'm going to say the real features is equal to feature extractor, right? You know, that's a cool name. You don't go in for, a root canal. You go in for an extraction. I want to define what the fake features are, right? Feature extractor high res fake. Nice. All right, so now we've basically what we've done is we've passed these into kind of the first chunk of VGG19, right? The static model, or so to speak, static model. And we're interpreting whatever input's being processed, and then we're looking at kind of like what features are being discovered, right? The first couple of sets in any neural network, first couple of layers in a neural network are for features, right? It's to understand what goes into the image, right? Is anything useful in the image? Excuse me, it's all that talking, man. Sometimes you just wish I would be quiet. Oh no, I don't want you to run. Stop. Okay, good. You complain if I don't. Right, so now we've gathered the extracted features and we understand what's going into the neural net images, right? Now we have to kind of determine what to do with this, right? We have to say, well, we got all this information. Now what? Now we got to train the generator, right? The trained generator is just sitting there creating fake images, not actually learning anything. So, we got to teach it. So I'm going to say generator 0 grad. Again, same process, but except now we have generator content loss. Right? That's going to be equal to content criterion and high res fake. And of course, we need to do the high res real. And then here's where the slight trick comes into play. The wow, that's a real doozy. We're going to do this 006, which we'll call alpha. Right? It's an alpha value. Or since we're in machine learning, it doesn't matter because no one keeps the same lettering system or notation at all. We can call it theta if we want. It doesn't matter to me. I'm just talking to myself out here. So 0.06 gets multiplied by the content criterion for our fake features, right? We've created these features, we've extracted the data from the images, and we're doing something with it. And here it is. That was the whole reason that we created a static model. And there's the police in this situation, or not the police, the lifeguard. I don't know, some higher authority that's above the cops and the robbers, right? This is the holy grail of reasoning that this model kind of works, and how it doesn't actually blow itself to smithereens, right? Of course, this value can be finished with, but I think everyone's kind of decided on 0.006. Everywhere I see it's 0.006, so I'm not going to change it. If anyone is feeling lucky or brave, they can go ahead and change it. I'm not going to stop you. More power to you, brother. All right. couple more lines. So of course, now that you've figured out, okay, so now what? We do generator content backwards, then optimization step, right? Ha ha. That's where you're wrong. We don't do that. We're going to do something even more crazy. We're going to say generator, and then we're going to calculate the adversarial loss. But Monish, that's insane. You can't do that. So then we're like, okay, well, it's fine. Don't even sweat about it. Okay, we're just going to say discriminator, right? We want to figure out what the discriminator thinks about high resolution. I want to say high resolution fake, but here's the trick. Here's the trick. We're going to say it's actually real, right? We're going to say that whatever image is being created is actually real, right? And this is where we start kind of interpreting whatever output that a discriminator creates as being, helping the generator, right? This is the holy grail of the GAN right here. This one line, right, that defines the GAN. Everything else is complete, garbage. You don't need to. You just ignore everything, delete it, Control Alt Delete, Alt F7, whatever it is. Delete system 32. This is the whole grail of GANs, and that's kind of what defines what an adversarial neural network is, right? It's trying to have a neural network understand that what it's being produced is actually correct, but you need to change it such that it can be correct, right? Like you can classify it as correct, even if it's close to being correct. It needs to be classified as correct by a discriminator, right? And that's this is literally where the cops and the robbers meet. Now you're saying, okay, now you do the whole thing, right? You have to create one more variable because if I don't do that, it's just going to look ugly. So now we're just like, okay, so you take the content loss, right, and you multiply it by 0.001, which is another alpha value, or since we already have an alpha value, we'll call it beta value. And we're going to say generator, what happened to you? Why are you not there? There you go. I'll just copy and paste you, yeah. Right? So now you're telling me, well, Monish, what the heck? You had adversarial loss, and then you just multiply 0.001, so it's like less than a % worth of importance. Well, that's not true. It's a value that we've determined brings the right balance between having the discriminator overpowering the generator, right? Because the discriminator technically is a more powerful model, right? In an ideal world, they'd be equals, but they're not because their jobs are very different. Right? In a discriminator, we're condensing information, right? And by condensing information, we can extract a lot more at each layer. A generator is not doing that much condensing, right? It's actually expanding data. So it's doing the exact opposite of what a generator is doing, right? And so some people like to call these an autoencoder. That's another fancy word, but this is not an autoencoder. This is a GAN. Autoencoders are different, right? In fact, autoencoders, I argue that it came from GANs, but anyways, that's besides the point. And no one's here to argue it, so haha, I win. So now is where we do this whole backwards, bend over backwards and pray to somebody that it works. Otherwise, I'm going to be sad. All right, hallelujah. If we run it, and if it doesn't crash, if I can get at least one epoch in, I'll say it's good. We're golden. We have struck gold, oil. I don't know. I'm really dated with these references. I don't know anything. But so as long as it doesn't crash, I'm happy. I don't really care after that. So it doesn't crash. So actually, I've tried this one time. It takes so it says 38 hours to finish the entire run. So if you have that much patience, go for it on Google Colab. Granted, you're gonna have to sit there and babysit Chrome so it doesn't time out. But good for you if you can. But instead of everyone sitting there and watching their paint dry and just twiddling their thumbs, I did a lot of the work for you guys, so you should be thankful for me. Let's see if I can open it up, please. No, that's not it. Where are you? Oh, here you are. Yes, yes, yes. I have made something, and it's beautiful. So real quick, let me just show you guys what I did differently, so that you guys, if you guys are interested in, can go do the exact same mistakes that I made. So our low resolution is actually gonna be 112, mainly because I have two GPUs and I'm able to do it. So haha, loser. But uh, another reason is just because again, Google Colab has one GPU and that too is already running really slow. So why would I want to bog it down even more? But so yeah, this is kind of all the data. I did it over multiple epochs, so you can't really see that much. But the main thing I want to show you guys is the results, right? What is all of this work led to, right? What is the point of all of this at the end of the day? And I'm telling you, you will be surprised. So up here we're going to have actual model of what the actual model produces, right? What the model I have produces. It's beautiful glory, right? Look at that. You can see the crisp lines. You can see each and every step. I think I don't know if it's a brick or not. It's a step. I agree to disagree with myself. Um, this is kind of that's it. That's what you get. It's beautiful. It's arguably one of masterpiece. Mozart would be jealous. I mean Leonardo da Vinci or Monet. That's who I was thinking. Monet. Yeah, he would be jealous. Here's kind of what we're competing against. So this is an interpolation. I think this is using bicubic or bilinear, one of those two, to do this interpolation. And you can see it's clearly fuzzy. There's no detail. There's very little in terms of definition. And so you lose out a lot of this kind of, you can see that like the railing doesn't look like a railing. It looks like, like one of those pipe cleaners. Yeah, it looks like a pipe cleaner. From elementary school, we used to make like robots and stuff with. And then here's the real truth, right? How the real output of what this is. If you want, I can do something special, and please don't kill my computer because I will be very sad. But if you guys want to, you can copy this URL. Here, let me just try and type it out. http://2c5c8166. Oh, that's not 6. 8166. Oh, almost the devil's number. Jesus. One more number and that would have been it. ngrok.io. Yes. Try it. Try it out. Yeah, I think it should work. Yeah, it kind of works. Cool. Yeah, you guys can go see the data for yourselves. Basically, you can see different images, which is kind of cool. So I don't know what that is. I think it's a crocodile or an alligator. I don't know the difference. I just know one comes in a catchy song and the other one doesn't. Yeah, you can see also another example of bicubic and you guys are really going ham at this one. How many open? Oh, 6. 6 people are accessing my computer inappropriately. Never mind. Let's see. Yeah, but you guys can see that the definition of the tiles is very distinct. You can see that they're actual tiles, whereas here it's all the same. It's like PS1 graphics combined with the worst reshape textures. You got Minecraft over here, and you just got this. Yeah. So, anyways, that kind of wraps it up. Thank you everyone for sticking with it. I know it hasn't been easy, especially for me. This has kind of been very difficult. But I mean, I had fun at the end, at least. I hope everyone else did have fun. And yeah, if anyone wants to leave any feedback, I would love feedback. I'd also, if anyone wants to get into argument, that'd be cool too. Oh yeah, also I will post the model up on Piazza for those who are interested. It is 500 gigabytes. No, megabytes. Sorry, not gigabytes. Megabytes. So I don't know how Piazza is going to handle that. It's in documents. Here you are. No, I don't want you. No, stop. Just listen to me. Properties. Yeah. Oh, 5 megs. Never mind. We should be able to do it. So anyone can go and do this on their own. I will also post a GitHub link to the source code. I mean, you guys have this as well. And in fact, if you guys want to, okay, I'll stop you. If you guys are absolutely desperate to try out my model on stuff and make it explode, you guys can go here. And I think you can just say, what are you? Oh, no. Stop. I said stop. Listen, obey. Okay, there we go. So we can just go documents. I'm just going to say this. Yeah, that's fine. I don't care. Did it upload? Did I get the spinning circle of death? What is this? Yeah, okay, cool. It uploaded. Good to know. And so if I say this, excuse me, it's allergies. I don't have the coronavirus. Don't worry. The world is safe. Come on, buddy. All right. Let's refresh this and see the explosion happen. There you go. So I just made a simple script. I didn't really organize anything, but you can get like the fake. So this is the actual output, or this is the the output non-neural network, like the high resolution image. And this is a low resolution image. It's lower res because it's also like smaller tile, mainly because of, again, this hyperparameter up here, which says low resolution, which is 56. Oh, you remember this from Intel, Brian? Yeah, I know. This is like almost the exact same project that I worked on at Intel. Couple of differences. I'm not using ResNet 50 in my model. I'm using a different architecture. But this is the basis of kind of what we're doing. Yeah. So good eye, Brian. Good eye. Anyways, yeah, that's about it. Thank you, everyone. I hope everyone stays safe out there. It's kind of a wild, wild west. Although if you're into that, have fun. Other than that, nothing else. Thank you. Ooh, we should listen to some music. Where is that thingy majig? Yes. So I'm going to add VLC source. A lot of people are saying this is good music. I kind of agree. So I'm just going to say yes, transition, and then we're going to do. Thank you.